Here's a cool little probability puzzle involving some dice from the Utah Math Olympiad. Let's say we roll 4 fair 6-sided dice. The question is simple. What's the probability that the numbers rolled can be divided into 2 pairs which sum up to the same value? So, for example, a roll like this one would satisfy the criteria, because we can separate the numbers rolled into 2 groups of 2, those being 1 and 6 and 4 and 3, which both add up to the same number, that being 7 in this case. Whereas with a roll like this one, there's no way for us to divide these numbers in such a way. So, how do you think we should approach this problem? Here's your chance to pause the video if you'd like to take some time to think about it some more. Okay, let's start off by examining our sample space, which is just the set of all possible outcomes. We can clearly see that with 1 die, we have 6 possible outcomes. And with 2, there are 6 possible outcomes per die, and so 36 possible outcomes in total, or 6 squared. So, following the same logic, rolling 4 dice would result in 6 to the 4 possible outcomes, or 1,296. Now, we could just manually go through every one of these and look for all the ones that satisfy our criteria. But where's the fun in that? Plus, I'm not sure how many of you really want to watch a 2-hour video about dice. Let's instead partition our sample space into different categories based on the form that the unordered sample points take on, and then examine each case individually. So, what do I mean by that? Well, let's let a through d be distinct integers between 1 and 6. Now, notice that each of our sample points can only take on one of 5 forms. Either all 4 dice land on the same number, 3 dice land on the same number, and 1 lands on a different one, 2 dice land on the same number, and the other 2 dice also land on the same number that's different from the first, 2 dice land on the same number while the other 2 land on different numbers, or all 4 dice land on different numbers. Now, before we move on, one important thing to note is that we're dealing with permutations here, and so the order of our dice rolls matters. So outcomes like these 2, for example, are considered completely different sample points, even though they both fall under the same category and are made up of the same numbers. So just keep that in mind moving forward. Alright, let's start off with the first case, which should be simple enough. There are only 6 ways for all 4 dice to land on the same number. And no matter which number that ends up being, we'll clearly be able to divide them up into 2 pairs that add up to the same number, since, well, both sides will be identical. Okay, cool. We've found 6 sample points that satisfy our criteria so far. Let's keep going and look at the second case now. For this one, notice that regardless of how we end up dividing the numbers up, one side will always have a number being added to itself. And since the other side has that same number being added to a different one, then it's impossible for both sides to equal each other here. Meaning that there are no sample points in this category that will satisfy our criteria. Now, for case number 3, notice that there are only 2 ways for us to divide the numbers up. We can either pair the same numbers together, or we can pair the different ones together. Pairing the same ones together makes it impossible for the sums to equal each other. But fortunately for us, if we pair the different ones together, then both sides become identical, and thus the sums will always be equal. Which means that every sample point of this form will satisfy our criteria. The only question now is, how many different sample points of this form are there? Well, since we're dealing with permutations, the first thing to note is that there are 6 ways to rearrange this type of sample point, which we can verify using the binomial coefficient. And since we're looking to pick 2 different numbers from a set of 6, then we can use the binomial coefficient again and see that there are 15 ways to select different values for a and b. Multiplying these together tells us that there are 90 different sample points of this form, all of which being able to satisfy our criteria. With case number 4, things start to get a bit tricky. The first thing to notice is that if A is paired with B, which implies that the other A is paired with C, then there's no way for the sums to equal each other, since, well, B and C aren't equal. But what if A is paired with the other A? Could the sums be equal in this case? Well, A plus A is just 2A, which we know must be even. And since A can be any integer between 1 and 6, then for the sums to be equal, B plus C needs to add up to at least one of the following. Now, without loss of generality, let's assume that B is less than C. With a quick manual search from our end, it's not too difficult to find all the solutions to these equations, with the first and last equations in particular having no solutions, and the third and fourth equations having 2 solutions each. Okay, so there are 6 unordered sample points that will satisfy our criteria in this case. And notice that I said unordered sample points, because we still need to consider all the ways in which we can shuffle the numbers around within each of these outcomes. Now, typically the number of ways to permute 4 values is 4 factorial, but since 2 of our values are duplicates, then we need to divide this number by 2 factorial. And so there are 12 ways to rearrange this type of sample point, meaning the total number of sample points satisfying our criteria under this category comes out to 6 times 12, or 72. Now, finally, with case number 5, there's no real point in trying to figure out how we can divide these numbers up. Since they're all different from one another, this process would be trivial. So let's instead try approaching from a different angle. Essentially, what we're looking for here are all the numbers that can be represented in at least 2 different ways as the sum of 2 distinct dice rolls. This isn't as difficult as it might sound. Let's just list out all the numbers that can be achieved by adding up 2 distinct dice rolls first. Now, we can go ahead and get rid of 3, 4, 10, and 11, because, like we already mentioned, we want the numbers to be representable in at least 2 different ways. As for the numbers 5, 6, 8, and 9, we can already see what our 4 distinct integers are going to be. But 7 has 3 different sums, so what should we do about that? Well, that just gives us 3 different equations to work with, each of which having their own set of 4 distinct integers. Therefore, we have 7 unordered sample points that will satisfy our criteria in this case. And just like with the previous case, these are just the unordered sample points, meaning we still have to consider all the ways that we can rearrange them, which this time around is in fact 4 factorial, or 24. And so the total number of sample points satisfying our criteria under this category must come out to 7 times 24, or 168. And there we go, we should be done now. Adding all of these numbers together tells us that there are 336 possible outcomes that will satisfy our criteria. Therefore, the probability we're looking for must be 336 over 6 to the 4, or 7 over 27. Now, you might have found another way of solving the puzzle. Maybe you let a through d be integers that aren't necessarily distinct and considered the following cases, where the probability we're looking for is the probability of either case 1 occurring, or case 2 occurring, or case 3 occurring. So, how can we solve the puzzle using this method? Let me know what you come up with in the comments below, and if you enjoyed the video and would like to show your support, don't forget to leave a like, and subscribe while you're at it for the many more math puzzles coming very soon.